Section 11 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kathleen. The Elements of Botany by Asa Gray. Stamens in particular. Androsecum is a technical name for the staminate system of a flower, that is, for the stamens taken together, which it is sometimes convenient to use. The preceding section has dealt with modifications of the flower pertaining mainly to calyx and corolla. Those relating to the stamens are now to be indicated. First, as to insertion, or place of attachment. The stamens usually go with the petals. Not rarely they are at base epipetalous, that is, inserted on or adnate to the corolla, as in Fig. 283. Illustration: Fig. 283, corolla of Morning Glory laid open, to show the 5 stamens inserted on it, near the base. When free from the corolla, they may be hypogynous, inserted on the receptacle under the pistil or gynoecium. Perigynous, inserted on the calyx, that is, with the lower part of filament adnate to the calyx tube. Epigynous, borne apparently on the top of the ovary, all which is explained in Fig. 270 to 274. Illustration: Fig. 284. Style of a lady's slipper, cypripedium, and stamens united with it. A. The anthers of the 2 good stamens. St. An abortive stamen, what should be its anther changed into a petal-like body. Stig. The stigma. Gynandrous is another term relating to insertion of rarer occurrence, that is, where the stamens are inserted on, in other words, adnate to, the style, as in lady's slipper, Fig. 284, and in the orchis family generally. In relation to each other, stamens are more commonly distinct, that is, without any union with each other, but when united. The following technical terms of long use indicate their modes of mutual connection. Monadelphous, from 2 Greek words meaning in one brotherhood, when united by their filaments into one set, usually into a ring, or cup below, or into a tube, as in the mallow family, Fig. 286. The passion flower, Fig. 260, the lupine, Fig. 287, and in lobelia, Fig. 285. Illustration: Fig. 285, flower of Lobelia cardinalis, cardinal flower, corolla making approach to the ligulate form, filaments St. monadelphous, and anthers A. syngenesius. Illustration: Fig. 286. Flower of mallow, with calyx and corolla cut away, showing monadelphous stamens. Fig. 287. Monadelphous stamens of lupine. 288. Diadelphous stamens, 9 in 1, of a pea blossom. Diadelphous, meaning in 2 brotherhoods, when united by the filaments into 2 sets, as in the pea and most of its near relatives. Fig. 288. Usually 9 in one set, and 1 in the other. Triadelphous, 3 brotherhoods, when the filaments are united in 3 sets, or clusters, as in most species of Hypericum. Pentadelphous, 5 brotherhoods, when in 5 sets, as in some species of Hypericum and in American linden, Fig. 277, 289. Polyadelphous, many or several brotherhoods, is the term generally employed when these sets are several, or even more than 2, and the particular number is left unspecified. These terms all relate to the filaments. Syngenesius is the term to denote that stamens have their anthers united, coalescent into a ring or tube, as in lobelia, Fig. 285, in violets, and in all of the great family of Compositae. Their number, in a flower, is commonly expressed directly, but sometimes adjectively, by a series of terms which were the name of classes in the Linnaean artificial system, of which the following names, as also the preceding, are a survival: monandrous, i.e., solitary stamened, when the flower has only 1 stamen; diandrous, when it has 2 stamens only; triandrous, when it has 3 stamens; tetrandrous when it has 4 stamens, pentandrous when it has 5 stamens, hexandrous when with 6 stamens, and so on to polyandrous when it has many stamens or more than a dozen. Illustration: Figure 289, one of the 5 stamen clusters of the flower of American linden, with accompanying scale. The 5 clusters are shown in section in the diagram of this flower, Figure 277. Figure 290, 5 ginseneous stamens of a coreopsis. 291, same, with the tube laid open and displayed. For which terms see the glossary. They are all Greek numerals prefixed to andria, from the Greek, which Linnaeus used for androsecum, and are made into an English adjective, androus. 2 other terms, of same origin, designate particular cases of number 4 or 6 in connection with unequal length, namely, the stamens are didynamous when, being only 4, they form 2 pairs, one pair longer than the other, as in the trumpet creeper, in Gerardia, Fig. 263, etc. Tetradynamos when, being only 6, 4 of them surpass the other 2, as in the mustard flower and all the cruciferous family, Fig. 235. The filament is a kind of stalk to the anther, commonly slender or thread-like. It is to the anther nearly what the petiole is to the blade of a leaf. Therefore it is not an essential part. As a leaf may be without a stalk, so the anther may be sessile, or without a filament. Illustration: Figure 292. Stamen of Isopyrum, with innate anther. 293. Of tulip tree, with adnate and extorse anther. 294. Of evening primrose, with versatile anther. The anther is the essential part of the stamen. It is a sort of case, filled with a fine powder, the pollen, which serves to fertilize the pistil, so that it may perfect seeds. The anther is said to be innate, as in Fig. 292, when it is attached by its base to the very apex of the filament, turning neither inward nor outward. Adnate, as in Fig. 293, when attached as it were by one face, usually for its whole length, to the side of a continuation of the filament, and versatile, as in Fig. 294, when fixed by or near its middle only to the very point of the filament, so as to swing loosely, as in the lily, in grasses, etc. Versatile or adnate anthers are intorse or incumbent, when facing inward, that is, toward the center of the flower, as in magnolia, water lily, etc. Extorse, when facing outwardly, as in the tulip tree. Rarely does a stamen bear any resemblance to a leaf, or even to a petal or flower leaf. Nevertheless, the botanist's idea of a stamen is that it answers to a leaf developed in a peculiar form and for a special purpose. In the filament he sees the stalk of the leaf, in the anther, the blade. The blade of a leaf consists of 2 similar sides. So the anther consists of 2 lobes or cells, one answering to the left, the other to the right, side of the blade. The 2 lobes are often connected by a prolongation of the filament, which answers to the mid-rib of a leaf. This is called the connective. This is conspicuous in Fig. 292, where the connective is so broad that it separates the 2 cells of the anther to some distance. Illustration: Fig. 295. Diagram of the lower part of an anther, cut across above, and the upper part of a leaf, to show how the one answers to the other, the filament to petiole, the connective to midrib, the 2 cells to the right and left halves of the blade. A simple conception of the morphological relation of an anther to a leaf is given in Fig. 295. An ideal figure, the lower part representing a stamen with the top of its anther cut away, the upper, the corresponding upper part of a leaf. So anthers are generally 2-celled, but as the pollen begins to form in 2 parts of each cell, the anterior and the posterior, sometimes these 2 strata are not confluent, and the anther even at maturity may be 4-celled, as in moonseed, Fig. 296, or rather, In that case, the word cell being used for each lateral half of the organ, it is two-celled, but the cells bilocellate. Illustration: Fig. 296. Stamen of moonseed, with anther cut across. This four-celled, or rather four-locellate. Fig. 297. Stamen of Penstemon pubescens, the two anther cells diverging, and almost confluent. Fig. 298. Stamen of Mallow, the anther supposed to answer to that of Fig. 297, but the cells completely confluent into one. Fig. 299. Stamen of Globe Amaranth, very short filament bearing a single anther cell. It is open from top to bottom, showing the pollen within. Illustration: Fig. 300 to 305. Stamens of several plants of the Labiate or mint family. Fig. 300 of Monarda. The two anther cells with bases divergent so that they are transverse to the filament, and their contiguous tips confluent, so as to form one cell opening by a continuous line. Fig. 301 of a Calamintha. The broad connective separating the two cells. Fig. 302 of a sage, Salvia texana, with a long and slender connective resembling forks of the filament, one bearing a good anther cell, the other an abortive or poor one. Fig. 303. Another sage, S. coccinea, with connective longer and more thread-shaped, the lower fork having its anther cell wholly wanting. Fig. 304 of a white sage, Audibertia grandiflora, the lower fork of connective a mere vestige. Fig. 305 of another white sage, A. stachioides, the lower fork of connective suppressed. But anthers may become one-celled, and that either by confluence or by suppression. By confluence, when the two cells run together into one, as they nearly do in most species of Penstemon. Fig. 297. More so in Monarda. Fig. 300, and completely in the Mallow. Fig. 298, and all the Mallow family. By suppression in certain cases the anther may be reduced to one cell or halved. In Globe Amaranth. Fig. 299, there is a single cell without vestige of any other. Different species of sage and of the white sages of California show various grades of abortion of one of the anther cells, along with a singular lengthening of the connective. Fig. 302 to 305. The splitting open of an anther for the discharge of its pollen is termed its dehiscence. Illustration: Fig. 306. Stamen with the usual dehiscence of anther down the side of each cell. Fig. 307. Stamen of Pyrola, cells opening by a terminal hole. Fig. 308. Stamen of Barberry, cells of anther each opening by an uplifted valve. As the figures show, this is commonly by a line along the whole length of each cell, either lateral, or, when the anthers are extors, often along the outer face, and when intors, along the inner face of each cell. Sometimes the opening is only by a chink, hole, or pore at the top, as in the Azalea pyrola. Fig. 307, etc. Sometimes a part of the face separates as a sort of trap door, or valve, hinged at the top, and opening to allow the escape of the pollen, as in the sassafras, spicebush, and barberry. Fig. 308. Pollen. This is the powdery matter, commonly of a yellow color, which fills the cells of the anther, and is discharged during blossoming, after which the stamens generally fall or wither away. Under the microscope it is found to consist of grains, usually round or oval, and all alike in the same species, but very different in different plants, so that the plant may sometimes be recognized from the pollen alone. Several forms are shown in the accompanying figures. Illustration: Fig. 309. Magnified pollen of a lily, smooth and oval. 310. Of Echinocystis, grooved lengthwise. 311. Of Sicyos, with bristly points and smooth bands. 312. Of musk plant, Mimulus, with spiral grooves. 313. Of succory, 12-sided and dotted. An ordinary pollen grain has two coats, the outer coat thickish, but weak, and frequently adorned with lines or bands, or studded with points. The inner coat is extremely thin and delicate, but extensible, and its cavity when fresh contains a thickish protoplasmic fluid, often rendered turbid by an immense number of minute particles that float in it. As the pollen matures this fluid usually dries up, but the protoplasm does not lose its vitality. When the grain is wetted it absorbs water, swells up, and is apt to burst, discharging the contents. But when weak syrup is used it absorbs this slowly, and the tough inner coat will sometimes break through the outer and begin a kind of growth, like that which takes place when the pollen is placed upon the stigma. Illustration: Figure 314. Magnified pollen of hibiscus and other mallow plants, beset with prickly projections. 315. Of circaea, with angles bearing little lobes. 316. Of evening primrose, the three lobes as large as the central body. 317. Of kalmia, 4 grains united, as in most of the heath family. 318. Of pine, as it were of 3 grains or cells united, the lateral empty and light. Some pollen grains are, as it were, lobed, as in Fig. 315, 316, or formed of 4 grains united, as in the heath family, Fig. 317. That of pine, Fig. 318, has a large rounded and empty bladder-like expansion upon each side. This renders such pollen very buoyant, and capable of being transported to a great distance by the wind. In species of acacia simple grains lightly cohere into globular pellets. In milkweeds and in most orchids all the pollen of an anther cell is compacted or coherent into one mass, called a pollen mass, or pollinium, plural pollinia. Fig. 319 to 322. Illustration: Fig. 319. Pollen, a pair of pollinia of a milkweed, Asclepias, attached by stalks to a gland, moderately magnified. Illustration: Fig. 320. Pollinium of an orchis, Habenaria, with its stalk attached to a sticky gland, magnified. 321. Some of the packets or partial pollinia, of which Fig. 320 is made up, more magnified. Illustration: Fig. 322. One of the partial pollinia, torn up at top to show the grains, which are each composed of 4, and highly magnified. End of section 11. Section 12 of Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kathleen. The Elements of Botany by Asa Gray. Pistils in particular. Angiospermous or ordinary gynosium. Gynosium is the technical name for the pistil or pistils of a flower taken collectively, or for whatever stands in place of these. The various modifications of the gynosium and the terms which relate to them require particular attention. The pistil, when only one, occupies the center of the flower. When there are 2 pistils, they stand facing each other in the center of the flower. When several, they commonly form a ring or circle, and when very numerous, they are generally crowded in rows or spirals on the surface of a more or less enlarged or elongated receptacle. Their number gives rise to certain terms, the counterpart of those used for stamens, 284, which are survivals of the names of orders in the Linnaean artificial system. The names were coined by prefixing Greek numerals to gynia, used for gynosium, and changed into adjectives in the form of gynous. That is, a flower is monogynous when it has a single pistil, whether that be simple or compound; digynous when it has only 2 pistils; trigynous when with 3; tetragynous with 4; pentagynous with 5; hexagynous with 6, and so on to polygynous with many pistils. The parts of a complete pistil, as already twice explained, 1.6, 2.36, are the ovary, the style, and the stigma. The ovary is one essential part. It contains the rudiments of seeds, called ovules. The stigma at the summit is also essential. It receives the pollen, which fertilizes the ovules in order that they may become seeds. But the style, commonly a tapering or slender column borne on the summit of the ovary, and bearing the stigma on its apex or its side, is no more necessary to a pistil than the filament is to the stamen. Accordingly, there is no style in many pistils. In these the stigma is sessile, that is, rests directly on the ovary, as in Fig. 326. The stigma is very various in shape and appearance, being sometimes a little knob, as in the cherry, Fig. 271, sometimes a point or small surface of bare tissue, as in Fig. 327 to 330, and sometimes a longitudinal crest or line, as in Fig. 324, 341 to 343, or it may occupy the whole length of the style, as in Fig. 331. The word pistil, Latin, pistillum, means a pestle. It came into use in the first place for such flowers as those of crown imperial, or lily, in which the pistil in the center was likened to the pestle, and the perianth around it to the mortar of the apothecary. A pistil is either simple or compound. It is simple when it answers to a single flower leaf, compound when it answers to 2 or 3, or a fuller circle of such leaves conjoined. Carpels. It is convenient to have a name for each flower leaf of the gynoecium, so it is called a carpel, in Latin carpellum or carpidium. A simple pistil is a carpel. Each component flower leaf of a compound pistil is likewise a carpel. When a flower has 2 or more pistils, these of course are simple pistils, that is, separate carpels or pistil leaves. There may be only a single simple pistil to the flower, as in a pea or cherry blossom, Fig. 271. There may be 2 such, as in many saxifrages, or many as in the strawberry. More commonly the single pistil in the center of a blossom is a compound one. Then there is seldom much difficulty in ascertaining the number of carpels or pistil leaves that compose it. The simple pistil, viewed morphologically, answers to a leaf blade with margins incurved and united where they meet, so forming a closed case or pod, the ovary, and bearing ovules at the suture or junction of these margins. A tapering upper portion with margins similarly enrolled is supposed to form the style, and these same margins, exposed at the tip or for a portion of the length, become the stigma. Compare, under this view, the 3 accompanying figures. Illustration: Fig. 323. An enrolled small leaf, such as in double-flowered cherry blossoms, is often seen to occupy the place of a pistil. Fig. 324. A simple pistil of Isopyrum, with ovary cut across, the inner ventral face turned toward the eye. The ovules seem to be borne on the ventral suture, answering to leaf margins. The stigma above seen also to answer to leaf margins. Fig. 325. Pod or simple pistil of Caltha or marsh marigold, which has opened and shed its seeds. So a simple pistil should have a 1-celled ovary, only 1 line of attachment for the ovules, a single style, and a single stigma. Certain variations from this normal condition which sometimes occur do not invalidate this morphological conception. For instance, the stigma may become 2-lobed or 2-ridged, because it consists of 2 leaf margins, as Fig. 324 shows. It may become 2-locellate by the turning or growing inward of one of the sutures, so as to divide the cavity. There are 2 or 3 terms which primarily relate to the parts of a simple pistil or carpel, and are thence carried on to the compound pistil, namely, ventral suture, the line which answers to the united margins of the carpel leaf, therefore naturally called a suture or seam, and the ventral or inner one, because in the circle of carpel leaves it looks inward or to the center of the flower. Dorsal suture is the line down the back of the carpel, answering to the mid-rib of the leaf, not a seam therefore, but at maturity many fruits, such as pea pods, open by this dorsal as well as by the ventral line. Placenta. A name given to the surface, whatever it be, which bears the ovules and seeds. The name may be needless when the ovules grow directly on the ventral suture, or from its top or bottom, but when there are many ovules there is usually some expansion of an ovule-bearing or seed-bearing surface, as is seen in our mandrake or podophyllum, Fig. 326. Illustration. Fig. 326. Simple pistil of podophyllum cut across, showing ovules borne on placenta. Fig. 327. Pistil of a saxifrage, of 2 simple carpels, or pistil leaves, united at the base only, cut across both above and below. Fig. 328. Compound 3 capillary pistil of common St. John's wort, cut across, the 3 styles separate. Fig. 329. The same of shrubby St. John's wort, the 3 styles as well as ovaries here united into one. Fig. 330. Compound 3 carpellary pistil of Tradescantia or spiderwort, the 3 stigmas as well as styles and ovary completely coalescent into one. A compound pistil is a combination of 2, 3, or a greater number of pistil leaves or carpels in a circle, united into one body, at least by their ovaries. The annexed figures should make it clear. A series of saxifrages might be selected, the gynosium of which should show every gradation between 2 simple pistils, or separate carpels, and their complete coalescence into one compound and 2-celled ovary. Even when the constituent styles and stigmas are completely coalescent into one, the nature of the combination is usually revealed by some external lines or grooves, or, as in Fig. 328 to 330, by the internal partitions, or the number of placentae. The simplest case of compound pistil is that with 2 or more cells and axile placentae, namely, with as many cells as there are carpels that have united to compose the organ. Such a pistil is just what would be formed if the simple pistils, 2, 3, or 5 in a circle, as the case may be, like those of a peony or stone crop, Fig. 224, 225, pressed together in the center of the flower, were to cohere by their contiguous parts. In such a case the placentae are naturally axile, or all brought together in the axis or center, and the ovary has as many discepiments, or internal partitions, as there are carpels in its composition, for these are the contiguous and coalescent walls or sides of the component carpels. When such pistils ripen into pods, they often separate along these lines into their elementary carpels. Illustration. Fig. 331, 332. Pistil of a sandwort, with vertical and transverse section of the ovary, free central placenta, 1-celled, with free central placenta. The commoner case is that of purslane, Fig. 272, and of the pink and chickweed families, Fig. 331, 332. This is explained by supposing that the partitions, such as those of Fig. 329, have early vanished or have been suppressed. Indeed, traces of them may often be detected in pinks. On the other hand, it is equally supposable that in the Primula family the free central is derived from parietal placentation by the carpels bearing ovules only at base, and forming a consolidated common placenta in the axis. Metella and Dionea help out this conception. Illustration. Fig. 333. Plan of a 1-celled ovary of 3 carpel leaves, with parietal placentae cut across below where it is complete. The upper part showing the top of the 3 leaves it is composed of, approaching, but not united. Fig. 334. Cross section of the ovary of frost weed, Helianthemum, with 3 parietal placentae bearing ovules. Fig. 335. Cross section of an ovary of Hybricum graveolens, the 3 large placentae meeting in the center, so as to form a 3-celled ovary. 336. Same in fruit, the placentae now separate and rounded, one-celled, with parietal placentae. In this not uncommon case it is conceived that the 2 or 3 or more carpal leaves of such a compound pistil coalesce by their adjacent edges, just as septal leaves do to form a gamosepalous calyx, or petals to form a gamopetalous corolla, and as is shown in the diagram, Fig. 333, and in an actual cross-section, Fig. 334, here each carpel is an open leaf, or with some introflexion, bearing ovules along its margins, and each placenta consists of the contiguous margins of 2 pistil leaves grown together. There is every gradation between this and the 3-celled ovary with the placentae in the axis, even in the same genus, sometimes even in different stages in the same pistil. Fig. 335, 336. Section 2. Gymnospermous gynoecium. The ordinary pistil has a closed ovary, and accordingly the pollen can act upon the contained ovules only indirectly, through the stigma. This is expressed in a term of Greek derivation, namely, angiospermous, meaning that the seeds are borne in a sac or closed vessel. The counterpart term is gymnospermous, meaning naked, seeded. This kind of pistil, or gynoecium, the simplest of all, yet the most peculiar, characterizes the pine family and its relatives. Illustration. Fig. 337. A pistil, that is, a scale of the cone of a larch at the time of flowering, inside view, showing its pair of naked ovules. Illustration. Fig. 338. Branchlet of the American arbor vitae, considerably larger than in nature, terminated by its pistillate flowers, each consisting of a single scale, an open pistil, together forming a small cone. Fig. 339. One of the scales or carpels of the last, removed and more enlarged, the inside exposed to view, showing a pair of ovules on its base, while the ordinary simple pistil is conceived by the botanist to be a leaf rolled together into a closed pod. Fig. 306. Those of the pine, larch, Fig. 337, cedar, and arbor vitae, Fig. 338, 339, are open leaves in the form of scales, each bearing 2 or more ovules on the inner face, next the base. At the time of blossoming, these pistil leaves of the young cone diverge, and the pollen, so abundantly shed from the staminate blossoms, falls directly upon the exposed ovules. Afterward the scales close over each other until the seeds are ripe. Then they separate that the seeds may be shed. As the pollen acts directly on the ovules, such pistil, or organ acting as pistil, has no stigma. In the yew and in torreya and ginkgo, the gynoecium is reduced to extremest simplicity, that is, to a naked ovule, without any visible carpel. In cycas the large naked ovules are borne on the margins or lobes of an obvious open leaf. All gymnospermous plants have other peculiarities, also distinguishing them as a class from angiospermous plants. End of section 12. Section 13 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kathleen. The Elements of Botany by Asa Gray. Ovules. Ovule, from the Latin meaning a little egg, is the technical name of that which in the flower answers to and becomes the seed. Illustration. Fig. 340. A cluster of ovules, pendulous on their funicles. Ovules are naked in gymnospermous plants, as just described. In all others they are enclosed in the ovary. They may be produced along the whole length of the cell or cells of the ovary, and then they are apt to be numerous, or only from some part of it, generally the top or the bottom. In this case they are usually few or single, solitary, as in Fig. 341 to 343. They may be sessile, i.e., without stalk, or they may be attached by a distinct stalk. The funicle or funiculus, Fig. 340. Illustration. Fig. 341. section of the ovary of a buttercup, lengthwise, showing its ascending ovule. Figure 342, section of the ovary of buckwheat, showing the erect ovule. Figure 343, section of the ovary of anemone, showing its suspended ovule. Considered as to then position and direction in the ovary, they are horizontal, when they are neither turned upward nor downward, as in Podophyllum, Fig. 326. Ascending, when rising obliquely upwards, usually from the side of the cell, not from its very base, as in the buttercup, Fig. 341, and the purslane, Fig. 272. Erect, when rising upright from the very base of the cell, as in the buckwheat, Fig. 342. Pendulous, when hanging from the side or from near the top, as in the flax, Fig. 270, and suspended, when hanging perpendicularly from the very summit of the cell, as in the anemone, Fig. 343. All these terms equally apply to seeds. In structure, an ovule is a pulpy mass of tissue, usually with one or two coats or coverings. The following parts are to be noted, namely, kernel or nucleus, the body of the ovule. In the mistletoe and some related plants, there is only this nucleus, the coats being wanting. Teguments, or coats, sometimes only one, more commonly two. When two, one has been called primine, the other secundine. It will serve all purposes to call them simply outer and inner ovule coats. Orifice or foramen, an opening through the coats at the organic apex of the ovule. In the seed, it is micropyle. Chalaza, the place where the coats and the kernel of the ovule blend. Hilum, the place of junction of the funiculus with the body of the ovule. Illustration: Fig. 344. Orthotropous, ovule of buckwheat. C. Hilum and chalaza. F. Orifice. Fig. 345. Campylotropous, ovule of a chickweed. C. Hilum and chalaza. F. Orifice. Fig. 346. Amphitropous, ovule of mallow. F. Orifice. H. Hilum. R. Raphe. C. chalaza. Fig. 347. Anatropous, ovule of a violet. The parts lettered as in the last. The kinds of ovules. The ovules in their growth develop in 3 or 4 different ways and thereby are distinguished into orthotropous or straight, those which develop without curving or turning, as in Fig. 344. The chalaza is at the insertion or base. The foramen or orifice is at the apex. This is the simplest, but the least common kind of ovule. Campylotropous or incurved, in which, by the greater growth of one side, the ovule curves into a kidney-shaped outline, so bringing the orifice down close to the base or chalaza, as in Fig. 345. Amphitropous or half inverted, Fig. 346. Here the forming ovule, instead of curving perceptibly, keeps its axis nearly straight, and, as it grows, turns round upon its base so far as to become transverse to its funiculus, and adnate to its upper part for some distance. Therefore in this case the attachment of the funiculus or stalk is about the middle, the chalaza is at one end, the orifice at the other. Illustration: Fig. 348 to 350. 3 early stages in the growth of ovule of a magnolia, showing the forming outer and inner coats which even in the later figure have not yet completely enclosed the nucleus. 351. Further advanced, and 352. Completely anatropous ovule. Fig. 353. Longitudinal section, and 354. Transverse section of 352. Illustration: Fig. 355. Same as 353. Enlarged, showing the parts in section: A. Outer coat. B. Inner coat. C. Nucleus. D. Raphe. Anatropous or inverted, as in Fig. 347. the commonest kind so called because in its growth it has as it were turned over upon its stalk, to which it has continued adnate. The organic base, or chalaza, thus becomes the apparent summit, and the orifice is at the base, by the side of the hilum or place of attachment. The adnate portion of the funiculus, which appears as a ridge or cord extending from the hilum to the chalaza, and which distinguishes this kind of ovule, is called the raphe. The amphitropous ovule, Fig. 346, has a short or incomplete raphe. Fig. 348 to 352 show the stages through which an ovule becomes anatropous in the course of its growth. The annexed two figures are sections of such an ovule at maturity, and Fig. 355 is Fig. 353 enlarged, with the parts lettered. End of section 13. Section 14 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kathleen. The Elements of Botany by Asa Gray. Modifications of the receptacle. Illustration. Figure 356. Longitudinal section of flower of Silene pennsylvanica, showing stipe between calyx and corolla. Figure 357. Flower of a cleome of the section Gynandropsis, showing broadened receptacle to bear petals, lengthened stipe below the stamens, and another between these and pistil. Figure 358. Pistil of geranium or crane's bill. Figure 357. The same, ripe, with the 5 carpels splitting away from the long beak, carpophore, and hanging from its top by their recurving styles. The torus or receptacle of the flower. Figure 237. Figure 223 is the portion which belongs to the stem or axis. In all preceding illustrations it is small and short, but it sometimes lengthens, sometimes thickens, or variously enlarges, and takes on various forms. Some of these have received special names, very few of which are in common use. A lengthened portion of the receptacle is called a stipe. This name, which means simply a trunk or stalk, is used in botany for various stalks, even for the leaf stalk in ferns. It is also applied to the stalk or petiole of a carpel, in the rare cases when there is any, as in gold thread. Then it is technically distinguished as the capor, when there is a stalk, or lengthened internode of receptacle, directly under a compound pistil, as in Stanleya and some other crucifera. It is called a gynophore. When the stalk is developed below the stamens, as in the species of Silene, Fig. 356, it has been called an anthophore or gynophore. In Fig. 357, the torus is dilated above the calyx, where it bears the petals. Then there is a long internode, gynophore, between it and the stamens, then a shorter one, gynophore, between these and the pistil. A carpophore is a prolongation of receptacle or axis between the carpels and bearing them. Umbelliferous plants and geranium, Fig. 358, 359, afford characteristic examples. Illustration. Fig. 360. Longitudinal section of a young strawberry, enlarged. Fig. 361. Similar section of a young rosehip. Fig. 362. Enlarged and top-shaped receptacle of Nelumbium at maturity. Flowers with very numerous simple pistils generally have the receptacle enlarged so as to give them room, sometimes becoming broad and flat, as in the flowering raspberry, sometimes elongated, as in the blackberry, the magnolia, etc. It is the receptacle in the strawberry, Fig. 360, much enlarged and pulpy when ripe, which forms the eatable part of the fruit, and bears the small seed-like pistils on its surface. In the rose, Fig. 361, Instead of being convex or conical, the receptacle is deeply concave, or urn-shaped. Indeed, a rosehip may be likened to a strawberry turned inside out, like the finger of a glove reversed, and the whole covered by the adherent tube of the calyx. The calyx remains beneath in the strawberry. In Nelumbium of the water lily family, the singular and greatly enlarged receptacle is shaped like a top, and bears the small pistils immersed in separate cavities of its flat upper surface. Figure 362. Illustration. Figure 363. Hypogynous disc in orange. A disc is an enlarged low receptacle or an outgrowth from it. Hypogynous when underneath the pistil, as in rue and the orange, Figure 363, and perigynous when adnate to calyx tube, as in buckthorn, Figure 364, 365, and cherry, Figure 271, or to both calyx tube and ovary, as in hawthorn, Figure 273. A flattened hypogynous disc underlying the ovary or ovaries, and from which they fall away at maturity, is sometimes called a gynobase, as in the rue family. In some oraginous flowers, such as hound's tongue, the gynobase runs up in the center between the carpels into a carpophore. The so-called epigynous disc, or stylopodium, crowning the summit of the ovary in flowers of umbellifera, etc., cannot be said to belong to the receptacle. Illustration. Figure 364. Flower of a buckthorn showing a conspicuous perigynous disc. Figure 365. Vertical section of same flower. End of section 14.
Section 15 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Elements of Botany by Asa Gray. Section 13. Fertilization. The end of the flowers is attained when the ovules become seeds. A flower remains for a certain time, longer or shorter according to the species, in anthesis, that is, in the proper state for the fulfillment of this end. During anthesis the ovules have to be fertilized by the pollen, or at least some pollen has to reach the stigma, or in gymnospermy the ovule itself, and so set up the peculiar growth upon its moist and permeable tissue, which has for result the production of an embryo in the ovules. By this the ovules are said to be fertilized. The first step is pollination, or so to say, the sowing of the proper pollen upon the stigma, where it is to germinate. Adaptations for pollination of the stigma. These variations and ever interesting adaptations and processes are illustrated in the botanical textbook Structural Botany, Chapter 6, Section 4, also in a brief and simple way in Botany for Young People, How Plants Behave, so mere outlines only are given here. Sometimes the application of pollen to the stigma is left to chance, as in dioecious wind-fertilized flowers. Sometimes it is rendered very sure, as in flowers that are fertilized in the bud. Sometimes the pollen is prevented from reaching the stigma of the same flower, although placed very near to it. But then there are always arrangements for its transference to the stigma of some other blossom of the kind. It is among these last that the most exquisite adaptations are met with. Accordingly, some flowers are particularly adapted to close or self-fertilization, others to cross-fertilization, some for either according to circumstances. Close fertilization occurs when the pollen reaches and acts upon a stigma of the very same flower. This is also called self-fertilization, or less closely upon other blossoms of the same cluster or the same individual plant. Cross-fertilization occurs when ovules are fertilized by pollen of other individuals of the same species. Hybridization occurs when ovules are fertilized by pollen of some other necessarily some nearly related, species. Close fertilization would seem to be the natural result of ordinary hermaphrodite flowers, but it is by no means so in all of them. More commonly the arrangements are such that it takes place only after some opportunity for cross-fertilization has been afforded. But close fertilization is inevitable in what are called cleistogamous flowers, that is, in those which are fertilized in the flower bud, while still unopened. Most flowers of this kind, indeed, never open at all, but the closed floral coverings are forced off by the growth of the precociously fertilized pistil. Common examples of this are found in the earlier blossoms of Specularia perfoliata, in the later ones of most violets, especially the stemless species, in our wild jewel weeds or impatiens, in the subterranean shoots of Amphicarpia. Every plant which produces these cleistogamous or bud-fertilized flowers bears also more conspicuous and open flowers, usually of bright colors. The latter very commonly fail to set seed, but the former are prolific. Cross-fertilization is naturally provided for in dioecious plants, is much favored in monoecious plants, and hardly less so in dichogamous and in heterogonous flowers. Cross-fertilization depends upon the transportation of pollen, and the two principal agents of conveyance are winds and insects. Most flowers are in their whole structure adapted either to the one or to the other. When fertilizable or anemophilous flowers are more commonly dioecious or monoecious, as in pines and all coniferous trees, oaks and birches and sedges, yet sometimes hermaphrodite, as in plantains and most grasses. They produce a superabundance of very light pollen, adapted to be wind-borne, and they offer neither nectar to feed winged insects, nor fragrance nor bright colors to attract them. Insect fertilizable or entomophilous flowers are those which are sought by insects, for pollen or for nectar or for both. Through their visits pollen is conveyed from one flower and from one plant to another. Insects are attracted to such blossoms by their bright colors, or their fragrance, or by the nectar, the material of honey, there provided for them. While supplying their own needs, they carry pollen from anthers to stigmas, and from plant to plant, thus bringing about a certain amount of cross-fertilization. Willows and some other dioecious flowers are so fertilized, chiefly by bees. But most insect-visited flowers have the stamens and pistils associated either in the same or in contiguous blossoms. Even when in the same blossom, anthers and stigmas are very commonly so situated that under insect visitation some pollen is more likely to be deposited upon other than upon own stigmas, so giving a chance for cross as well as for close fertilization. On the other hand, numerous flowers of various kinds have their parts so arranged that they must almost necessarily be cross-fertilized or be barren, and are therefore dependent upon the aid of insects. This aid is secured by different exquisite adaptations or contrivances, which would need a volume for full illustration. Indeed, there is a good number of volumes devoted to this subject. Footnote: beginning with one of C.C. Springle in 1793, and again in our day with Darwin on the various contrivances by which orchids are fertilized by insects, and in succeeding works. End footnote. Some of the adaptations which favor or ensure cross-fertilization are peculiar to the particular kind of blossom. Orchids, milkweeds, kalmia, iris, and papilionaceous flowers each have their own special contrivances, quite different for each. Irregular flowers, and especially irregular corollas, are usually adaptations to insect visitation. So are all nectaries, whether hollow spurs, sacs, or other concavities in which nectar is secreted, and all nectariferous glands. Moreover, there are two arrangements for cross-fertilization common to hermaphrodite flowers in various different families of plants, which have received special names: dichogamy and heterogamy. Dichogamy is the commoner case. Flowers are dichogamous when the anthers discharge their pollen either before or after the stigmas of that flower are in a condition to receive it. Such flowers are Proterandrous, when the anthers are earlier than the stigmas, as in gentians, campanula, epilobium, etc. Proterogynous, when the stigmas are mature and moistened for the reception of pollen, before the anthers of that blossom are ready to supply it, and are withered before that pollen can be supplied. Plantains and ribworts, mostly wind-fertilized, are strikingly proterogynous. So is amorpha, or pawpaws, scrophularia, and in a less degree the blossom of pears, hawthorns, and horse chestnut. In sabbatia, the large-flowered species of epilobium, and strikingly in clerodendron, the dichogamy is supplemented and perfected by movements of the stamens and style, one or both adjusted to make sure of cross-fertilization. Heterogony. This is the case in which hermaphrodite and fertile flowers of two sorts are produced on different individuals of the same species, one sort having higher anthers and lower stigmas, the other having higher stigmas and lower anthers. Thus reciprocally disposed, a visiting insect carries pollen from the high anthers of the one to the high stigma of the other, and from the low anthers of the one to the low stigma of the other. These plants are practically as if dioecious, with the advantage that both kinds are fruitful. Houstonia and Michela, or partridge berry, are excellent and familiar examples. These are cases of heterogone dimorphism, the relative lengths being only short and long reciprocally. Heterogone trimorphism, in which there is a mid-length as well as a long and short set of stamens and style, occurs in Lythrum salicaria and some species of oxalis. There must be some essential advantage in cross-fertilization or cross-breeding. Otherwise, all these various, elaborate, and exquisitely adjusted adaptations would be aimless. Doubtless the advantage is the same as that which is realized in all the higher animals by the distinction of sexes. Action of pollen and formation of the embryo. Pollen growth. A grain of pollen may be justly likened to one of the simple bodies, spores, which answer for seeds in cryptogamous plants. Like one of these, it is capable of germination. When deposited upon the moist surface of the stigma, or in some cases even when at a certain distance, it grows from some point, its living inner coat breaking through the inner outer coat, and protruding in the form of a delicate tube. This, as it lengthens, penetrates the loose tissue of the stigma and of the loose conducting tissue in the style, feeds upon the nourishing liquid matter there provided, reaches the cavity of the ovary, enters the orifice of an ovule, and attaches its extremity to a sac, or the lining of a definite cavity, in the ovule called the embryo sac. Origination of the embryo. A globule of living matter in the embryo sac is formed, and is in some way placed in close proximity to the apex of the pollen tube. It probably absorbs the contents of the latter. It then sets up a special growth, and the embryo or rudimentary plantlet in the seed is the result. End of section 15.
Section 16 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Corinne LePage. The Elements of Botany by Asa Gray. Section 14. The Fruit. Its nature. The ovary matures into the fruit. In the strictest sense, the fruit is the seed vessel, technically named the pericarp, but practically it may include other parts organically connected with the pericarp. Especially the calyx, or a part of it, is often incorporated with the ovary, so as to be undistinguishably a portion of the pericarp, and it even forms along with the receptacle the whole bulk of such edible fruits as apples and pears. The receptacle is an obvious part in blackberries, and is the whole edible portion in the strawberry. Also a cluster of distinct carpels may, in ripening, be consolidated or compacted so as practically to be taken for one fruit. Such are raspberries, blackberries, the magnolia fruit, etc. Moreover, the ripened product of many flowers may be compacted or grown together so as to form a single compound fruit. Its kinds have therefore to be distinguished. Also, various names of common use in descriptive botany have yet to be mentioned and defined. In respect to composition, accordingly, fruits may be classified into simple, those which result in the ripening of a single pistil and consist only of the matured ovary either by itself, as in a cherry, or with a calyx tube completely incorporated with it, as in a gooseberry or cranberry. Aggregate, when a cluster of carpels of the same flower are crowded into a mass, as in raspberries and blackberries. Figure 366. Forming fruit capsule of Gaultheria, with calyx thickening around its base. Section of same mature, the berry-like calyx nearly enclosing the capsule. Figure 368. Section of a part of a strawberry. Figure 369. Similar section of part of a blackberry. Figure 370. One of its component simple fruits, drupe, in section, showing the pulp, stone, and contained seed, more enlarged. Accessory, or anthocarpus. When the surroundings or supports of the pistil make up a part of the mass, as does the loose calyx changed into a fleshy and berry-like envelope of our wintergreen and buffalo berry, which are otherwise simple fruits. In an aggregate fruit, such as the strawberry, the great mass is receptacle, and in the blackberry the juicy receptacle forms the central part of the savory mass. Multiple, or collective, when formed from several flowers consolidated into one mass, of which the commonplace receptacle or axis in inflorescence, the floral envelopes, and even bracts, etc., make a part. A mulberry, which superficially much resembles a blackberry, is of this multiple sort. A pineapple is another example. In respect to texture or consistence, fruits may be distinguished into three kinds, viz. Fleshy fruits, those which are more or less soft and juicy throughout; stone fruits or drupaceous, the outer part fleshy like a berry, the inner hard or stony like a nut; and dry fruits, those which have no flesh or pulp. In reference to the way of disseminating the contained seed, fruits are said to be indehiscent when they do not open at maturity. Fleshy fruits and stone fruits are of course indehiscent. The seed becomes free only through decay or by being fed upon by animals. Those which escape digestion are thus disseminated by the latter. Of dry fruits many are indehiscent, and these are variously arranged to be transported by animals. Some burst irregularly, many are dehiscent, that is, they split open regularly along certain lines and discharge the seeds. A dehiscent fruit almost always contains many or several seeds, or at least more than one seed. Figure 371. Leafy shoot and berry cut across of the larger cranberry, Vaccinium macrocarpon. Figures 372 and 373. Pepo of gourd in section. One carpel of same in diagram. Figure 374. Longitudinal and transverse sections of a pear, pome. The principal kinds of fruit which have received substantive names and are of common use in descriptive botany are the following. Of fleshy fruits, the leading kind is the berry, such as the gooseberry and currant, the blueberry and cranberry, the tomato and the grape. Here the whole flesh is soft throughout. The orange is a berry with a leathery rind. The pepo, or gourd fruit, is a hard-rinded berry belonging to the gourd family, such as the pumpkin, squash, cucumber, and melon. The pome is a name applied to the apple, pear, and quince, fleshy fruits like a berry, but the principal thickness is calyx, only the papery pods arranged in a star in the core really belonging to the carpels. The fruit of the hawthorn is a drupaceous pome, something between pome and drupe. Of fruits which are externally fleshy and internally hard, the leading kind is the drupe, or stone fruit, of which the cherry, plum, and peach are familiar examples. In this, the outer part of the thickness of the pericarp becomes fleshy or softens like a berry, while the inner hardens like a nut. From the way in which the pistil is constructed, it is evident that the fleshy part here answers to the lower, and the stone to the upper face of the component leaf. The layers or concentric portions of a drupe, or of any pericarp which is thus separable, are named when thus distinguishable into three portions: epicarp, the external layer, often the mere skin of the fruit; mesocarp, the middle layer, which is commonly the fleshy part; and endocarp, the innermost layer, the stone. But more commonly only two portions of a drupe are distinguished, and are named, the outer one, sarcocarp or exocarp, for the flesh, the first name referring to the fleshy character, the second to its being an external layer; and putamen or endocarp, the stone within. Figure 375. Longitudinal section of a peach, showing flesh, stone, and seed. The typical or true drupe is of a single carpel, but, not to multiply technical names, this name is extended to all such fruits when fleshy without and stony within, although of compound pistil, even to those having several or separable stones, such as the fruit of holly. These stones in such drupes, or drupaceous fruits, are called perennae, or nucules, or simply nutlets of the drupe. Of dry fruits, there are greater diversity of kinds having distinct names. The indehiscent sorts are commonly one-seeded. Figure 379. Akene of a buttercup, the same divided lengthwise to show the contained seed. Figure 378. Akene of virgin's bower, retaining the feathered style, which aids in dissemination. The akene, or acinium, is a small, dry, and indehiscent one-seeded fruit, often so seed-like in appearance that it is popularly taken for the naked seed. The fruit of the buttercup, or crowfoot, is a good example. Its nature as a ripened pistil, in this case a simple carpel, is apparent by its bearing the remains of a style or stigma, or a scar from which this has fallen. It may retain the style and use it in various ways for dissemination. The fruit of compositae, though not of a single carpel, is also an akene. In this case the pericarp is invested by an adherent calyx tube, the limb of which, when it has any, is called the pappus. This name was first given to the down like that of the thistle, but is applied to all forms under which the limb of the calyx of the compound flower appears. In lettuce, dandelion, and the like, the acinium, as it matures, tapers upwards into a slender beak, like a stalk to the pappus. Figure 379. Akene of mayweed, no pappus. Figure 380. That of its succori, its pappus a shallow cup. Figure 381. Of sunflower, pappus of 2 deciduous scales. Figure 382. Of sneezeweed, helenium, with its pappus of 5 scales. Figure 383. Of sow thistle, with its pappus of delicate downy hairs. Figure 384. Of the dandelion, its pappus raised on a long beak. A cremocarp, a name given to the fruit of Umbelliferae, consists as it were of a pair of akenes, united completely in the blossom, but splitting apart when ripe into the 2 closed carpels. Each of these is a mericarp or hemicarp, name seldom used. A utricle is the same as an akene, but with a thin and bladdery loose pericarp, like that of the goosefoot or pigweed. When ripe, it may burst open irregularly to discharge the seed, or it may open by a circular line all round, the upper part falling off like a lid, as in the amaranth. Figure 385. Fruit, cremocarp, of Osmorrhiza. The 2 akene-like ripe carpels separating at maturity from a slender axis or carpophore. Figure 386. Utricle of the common pigweed, Chenopodium album. Figure 387. Utricle, pyxis, of amaranth, opening all round, circumscissile. A caryopsis or grain is like an akene, with the seed adhering to the thin pericarp throughout, so that fruit and seed are incorporated into one body, as in wheat, Indian corn, and other kinds of grain. A nut is a dry and indehiscent fruit, commonly one-celled and one-seeded, with a hard crustaceous or bony wall, such as the cocoanut, hazelnut, chestnut, and the acorn. Here the involucre, in the form of a cup at the base, is called the cupule. In the chestnut, the cupule forms the burr; in the hazel, a leafy husk. Figure 388. Nut, acorn of the oak, with its cup or cupule. A samara, or key fruit, is either a nut or an akene, or any other indehiscent fruit, furnished with a wing like that of ash and elm. The maple fruit is a pair of keys. Dehiscent fruits or pods are of two classes, viz. Those of a simple pistil or carpel, and those of a compound pistil. Two common sorts of the first are named as follows. The follicle is a fruit of a simple carpel, which dehisces down one side only, i.e. by the inner or ventral suture. The fruits of marsh marigold, peony, larkspur, and milkweed are of this kind. Figure 389. Samara, or key of the white ash, winged at end. Figure 390. Samara of the American elm, winged all round. Figure 391. Pair of samaras of sugar maple. Figure 392. Follicle of marsh marigold, Caltha palustris. Figure 393. Legume of a sweet pea, opened. Figure 394. Loment or jointed legume of a tick trefoil, Desmodium. The legume or true pod, such as the pea pod, and the fruit of the leguminous or pulse family generally, is one which opens along the dorsal as well as the ventral suture. The two pieces in which it splits are called valves. A loment is a legume which is constricted between the seeds, and at length breaks up crosswise into distinct joints, as in Figure 394. The pods or dehiscent fruits belonging to a compound ovary have several technical names, but they all may be regarded as kinds of the capsule, the dry and dehiscent fruit of any compound pistil. The capsule may discharge its seeds through chinks or pores, as in the poppy, or burst irregularly in some part, as in lobelia, and in the snapdragon, but commonly it splits open, or is dehiscent, lengthwise into regular pieces called valves. Figure 395. Capsule of iris, with loculicidal dehiscence below cut across. Figure 396. Pod of a marsh St. John's wort, with septicidal dehiscence. Regular dehiscence in a capsule takes place in two ways, which are best illustrated in pods of 2 or 3 cells. It is either loculicidal, or splitting directly into the loculi or cells, that is, down the back or the dorsal suture of each cell or carpel, as in iris, or septicidal, that is, splitting through the partitions or septa, as in St. John's wort, rhododendron, etc. This divides the capsule into its component carpels, which then open by their ventral suture. Figure 397 and 398. Diagrams of the two modes. Figure 399. Diagram of a septifragal dehiscence of the loculicidal type. Figure 400. Same of the septicidal or marginicidal type. In loculicidal dehiscence, the valves naturally bear the partitions on their middle. In the septicidal, half the thickness of a partition is borne on the margin of each valve. See the annexed diagrams. A variation of either mode occurs when the valves break away from the partitions, these remaining attached in the axis of the fruit. This is called septifragal dehiscence. One form is seen in the Morning Glory. The capsules of rue, spurge, and some others are both loculicidal and septicidal, and so split into half carpellary valves or pieces. The salique is the technical name of the peculiar pod of the mustard family, which is two-celled by a false partition stretched across between two parietal placentae. It generally opens by two valves from below upward, and the placentae with the partition are left behind when the valves fall off. A silicle or pouch is only a short and broad salique, like that of the shepherd's purse. Figure 401. Silique of a cadmine or spring cress. Figure 402. Silicle of shepherd's purse. Figure 403. Same with one valve removed. Figure 404. Pyxis of purslane, the lid detaching. The pyxis is a pod which opens by a circular horizontal line, the upper part forming a lid, as in purslane, the plantain, henbane, etc. In these the dehiscence extends all round, or is circumscissile. So it does in amaranth, forming a one-seeded utricular pyxis. In Jeffersonia the line does not quite separate quite round, but leaves a portion for a hinge to the lid. Of multiple or collective fruits, which are properly masses of fruits aggregated into one body, as seen in the mulberry, pineapple, etc., there are two kinds with special names and of peculiar structure. Figure 405. A fig fruit when young. Figure 406. Same in section. Figure 407. Magnified portion in slice showing some of the flowers. Figure 408. A mulberry. Figure 409. One of the grains younger, enlarged, seen to be a pistillate flower with calyx becoming fleshy. Figure 410. Same with fleshy calyx cut across. The syconium or fig fruit is a fleshy axis or summit of stem, hollowed out and lined within by a multitude of minute flowers, the whole becoming pulpy and the common fig luscious. The strobile or cone is the peculiar multiple fruit of pines, cypresses, and the like, hence the name coniferae, vis-a-vis cone-bearing plants. As already shown, these cones are open pistils, mostly in the form of flat scales, regularly overlying each other and pressed together in a spike or head. Each scale bears one or two naked seeds on its inner face. When ripe and dry, the scales turn back or diverge, and in the pine the seed peels off and falls, generally carrying with it a wing, a part of the lining of the scale which facilitates the dispersion of the seeds by the wind. In arbor vitae, the scales of the small cone are few, but not very unlike the leaves. In cypress they are very thick at the top and narrow at the base, so as to make a peculiar sort of closed cone. In juniper and red cedar, the few scales of the very small cone become fleshy and ripen into a fruit which closely resembles a berry. Figure 411. Cone of a common pitch pine. Figure 412. Inside view of a separated scale or open carpel, one seed in place. Figure 413. The other seed. End of section 16. Recording by Corinne LePage.
Section 17 of the Elements of Botany. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Elements of Botany by Asa Gray. Section 15. The Seed. Seeds are the final product of the flower, to which all its parts and offices are subservient. Like the ovule from which it originates, a seed consists of coats and kernels. The seed coats are commonly two, the outer and the inner. Figure 414 shows the two in a seed cut through lengthwise. The outer coat is often hard or crustaceous, whence it is called the testa, or shell of the seed. The inner is almost always thin and delicate. The shape and the markings, so various in different seeds, depend mostly on the outer coat. Sometimes this fits the kernel closely. Sometimes it is expanded into a wing, as in the trumpet creeper, and occasionally this wing is cut up into shreds or tufts, as in the catalpa, or instead of a wing it may bear a coma, or tuft of long and soft hairs, as in the milkweed or silkweed. The use of wings or downy tufts is to render the seeds buoyant for dispersion by the winds. This is clear not only from their evident adaptation to this purpose, but also from the fact that winged and tufted seeds are found only in fruits that split open at maturity, never in those that remain closed. The coat of some seeds is beset with long hairs or wool. Cotton, one of the most important vegetable products, since it forms the principal clothing of the larger part of the human race, consists of the long and woolly hairs which thickly cover the whole surface of the seed. There are also crests or other appendages of various sorts on certain seeds. A few seeds have an additional but more or less incomplete covering outside of the real seed coats, called aril or arillus. The loose and transparent bag which encloses the seed of the white water lily is of this kind. So is the mace of the nutmeg, and also the scarlet pulp around the seeds of the waxwork, Celastrus, and strawberry bush, Euonymus. The aril is a growth from the extremity of the seed stalk or from the placenta when there is no seed stalk. A short and thickish appendage at or close to the hilum in certain seeds is called a caruncle or strophiole. The various terms which define the position or direction of the ovule, erect, ascending, etc., apply equally to the seed. So also the terms anatropous, orthotropous, campylotropous, etc., as already defined, and such terms as hilum or scar left where the seed stalk or funiculus falls away, or where the seed was attached directly to the placenta when there is no seed stalk. Raphe, the line or ridge which runs from the hilum to the chalaza in anatropous and amphitropous seeds. Chalaza, the place where the seed coats and the kernel or nucleus are originally connected. At the hilum in orthotropous and campylotropous seeds, at the extremity of the raphe or tip of the seed in other kinds. Micropyle, answering to the foramen or orifice of the ovule. Compare the accompanying figures and those of the ovules. The kernel or nucleus is the whole body of the seed within the coats. In many seeds the kernel is all embryo. In others a large part of it is the albumen. The albumen or endosperm of the seed is sufficiently characterized and its office explained in section 3, 31-35. The embryo or germ, which is the rudimentary plantlet and final result of blossoming, and its development and germination have been extensively illustrated in sections 2 and 3. Its essential parts are the radicle and the cotyledons. Its radicle or caulicle, the former is the term long and generally used in botanical descriptions, but the latter is the more correct one, for it is the initial stem which merely gives origin to the root. As to its position in the seed, always points to and lies near the micropyle. In relation to the pericarp, it is superior when it points to the apex of the fruit or cell, and inferior when it points to its base or downward. The cotyledons have already been illustrated as respect their number, giving the important distinction of dicotyledonous, polycotyledonous, and monocotyledonous embryos. Also as regards their thickness, whether foliaceous or fleshy, and some of the very various shapes and adaptations to the seed have been figured. They may be straight or folded or rolled up. In the latter case the cotyledons may be rolled up as it were from one margin, as in calycanthus, or from apex to base in a flat spiral, or they may be both folded, plicate, and rolled up convolute, as in sugar maple. In one very natural family, the cruciferæ, two different modes prevail in the way the two cotyledons are brought around against the radicle. In one series they are accumbent, that is, the edges of the flat cotyledons lie against the radicle. In other they are incumbent, or with the plane of the cotyledons brought up in the opposite direction, so that the back of one of them lies against the radicle. As to the situation of the embryo with respect to the albumen of the seed, when this is present in any quantity, the embryo may be the axile, that is, occupying the axis or center, either for most of its length, as in violet, barberry, and pine, and in these it is straight, but it may be variously curved or coiled in the albumen, as in helianthemum, in a potato seed or onion seed, and linden. Or it may be coiled around the outside of the albumen, partly or into a circle, as in chickweed and mirabilis. The latter mode prevails in campylotropous seeds. In the cereal grains, such as Indian corn and rice, and in all other grasses the embryo is straight and applied to the outside of the abundant albumen. The matured seed with embryo ready to germinate and reproduce the kind completes the cycle of the vegetable life in a phanerogamous plant, the account of which began with the seed and seedling. Section 17.